Okay, so hello everyone. I am Siddhartha Pramanik. I am a research scholar from the Department of Mathematics, IIT Kharagpur. So this is the first tutorial season of the course Introduction to Rings and Fields. So I will be solving some problems related to the content of first week. Meanwhile, if you have any doubt in between, you can unmute yourself and ask, or you can put it in the chat box. So before start solving the problems, let me mention some keywords of the week 1. So basically we have started with the definition of ring. Then we have saw some examples. Then the professor has defined subrings. After that, he has defined a special type of element known as units. And then he mentioned a special type of ring known as polynomial rings. And in polynomial ring, he has defined what is meant by monic polynomial, monomials, and degree of a polynomial, all those things. And then he has taught how to do division in polynomial rings. Okay, so in this course, ring means always, okay, first let me put this as assumptions. So in this course, ring means always commutative ring with identities. Commutative ring with unity or identity. And also our subring contains the identity of the bigger ring. So subrings contains the identity of the bigger ring. So keep these assumptions in your mind. Okay. So first I want to define one more special type of element which will be useful. So this is known as zero divisors. So, let me define this. So let R be a ring. So when a element in a ring is called a zero divisor. So first of all, a zero divisor should be a non-zero element. So a non-zero element, let's say A in R, is said to be a zero divisor if there exists another non-zero element, let's call it B in R, such that the product of A and B is 0. So since we are in a commutative ring, so AB is basically same as BA. So I am just mentioning A times B. So an element A is zero divisor if there exists another non-zero element B such that the product is 0. So let's see some examples. So let's take R as the ring Z mod 4Z. So we all know that this is basically 0 bar, 1 bar, 2 bar, 3 bar, right? So here you can check 2 bar is a zero divisor because 2 bar times 2 bar is basically 0 bar. Okay, so some facts about this. So if an element is unit, it cannot be a zero divisor. So an unit cannot be a zero divisor. So let's see why this is the case. So let A belongs to R is unit. So A be a unit in a ring R. So that means there exists another element B in R such that their product is 1, right? Now if A is a zero divisor, then there exists some non-zero element, let's say C in R, such that A times C is 0. Now here you multiply B, so AB equals to 1 and also BA equals to 1, right? So in this equation you multiply with B in the both sides. So B times A times C is equals to B times 0. So that means uh, C equals to 0. But this is violating that C is a non-zero element. So this is contradiction. So A cannot be a zero divisor. So units cannot be zero divisors. And the second fact is zero divisors cannot be units. Because of the same argument, you can check this. So from these two argument, the first one and second one can conclude that a non-zero element, it cannot be simultaneously unit and zero divisor. So a non-zero element cannot be simultaneously unit as well as zero divisor. Okay, so I hope this is clear. Now let me ask you, so in a ring, can it happen that element that is neither unit nor zero divisor? So let me write this. Does there exist elements in a ring which are neither unit nor a zero divisor? Nor zero divisor. Yeah, just think this for a few minutes. Yeah, you are right. So this is true. There can, so for example, if you take the ring integers, then there are infinitely many such elements. Okay, good. So with this, let me write down the first problem. So let R be a ring which has finitely many elements. Okay, so R is a finite ring. So in that case, these above situation which I have asked in 4, this cannot happen. So then prove that every non-zero element in R is either unit or zero divisor. First, I have mentioned that there are rings in which we can find non-zero elements which are neither unit nor zero divisor. But now I am saying that in a finite ring that cannot happen. So in a finite ring, every non-zero element is either unit or a zero divisor. So I hope you have understood the statement. So let's see a proof of this. So the important thing here is R is a finite ring. Okay. So let A belongs to R be a non-zero element. So what we have to prove here is A is either unit or a zero divisor. So if A is a unit, then we are done. So if A is unit, we have nothing to prove. Okay. So assume that A is not a unit. So in that case, we have to prove A is a zero divisor. So we need to prove A is a zero divisor. So we need to find a non-zero element B in R such that A times B is zero, right? That is from the definition. So now consider this function let's say f from R to R itself defined by f of R goes to A times R for R belongs to R. So basically we are just multiplying the elements of R with A. Now what can you say about this function? So is it bijective? So observe that we have assumed A is not a unit. So this means there does not exist any element B such that A times B equals to 1. So here uh, if you take the element 1, so it cannot have a preimage here, right? So then 1 belongs to R does not have any preimage in R because A is not a unit, right? So this means the function f is not surjective. So f is not surjective. Okay, I hope this is clear. Now from this we can conclude that thus f is not injective as well. So because R is finite. So R is a finite set and f is a function from R2 itself. So a function from finite set to itself is injective if and only if it is surjective and if and only if it is bijective, right? That is something you can do by yourself, or if you are unable to do, then you can come back to me later. I will do that proof. So for the time you just assume it. It's better let me give you as an exercise. So if is not injective, so that means uh, there exist two different elements let's say R1 not equals to R2 in R whose images are same, right? So f of R1 equals to f of R2. Now this implies A times R1 equals to A times R2, and from this you can write A times R1 minus R2 is equals to 0. Now R1 not equals to R2 means R1 minus R2 is non-zero. So we have found a non-zero element whose product with A is 0. So A is a zero divisor. So is it okay, or do you have any doubt in this? Okay. Okay, fine. So okay, so we are not using any fact from ring homomorphism. Okay, so we are just using that this is a function. We don't need ring homomorphism here. This is an well-defined function, right? Because R is a ring, so A times R is also in the ring R. We have just used the fact that R is a finite set. No, we are taking the same R. So why it is not a ring? No, no, I am saying one does not have any pre-image. So you cannot find an element R prime which image is 1 because A is not a unit. You cannot find an element R prime such that A R prime is equal to 1, right? So that means you cannot find an element such that f of R prime is 1. Did you got, or you still have doubt? Yeah, that is true for a ring homomorphism, but I am not using anything from ring homomorphism. I have just defined a function. That's all. So I hope you have understood. So let me go to the next problem. I think it is there. I think they will upload in the due course. Okay, so let me. Okay, R is in the image is no longer a ring, so it is just a function. It does not preserve the ring structure. Yeah, it did not preserve the ring structure. Yeah, it's just a simple function. It has no other property. It's just a function. Okay, so in a ring, let let R be a ring, and let's say U be the set of all units in R. So I'm just collecting all the units in R and I'm calling that set U. So then U forms a group with respect to the multiplication of the ring. Okay. So the set of all units in a ring forms a group with respect to multiplication. So let's see a solution of this quickly because it's very easy. So first of all, the identity element belongs to U because it is inverse of itself. So U is a non-empty set. So for a group, what we need to check? The closure, the associativity, identity element of the group exist or not, and inverses of all elements. So these are the four properties of a group. So let's try with the closure. So here let me write. So U is non-empty. Okay. So let U A and B belongs to U. So we need to prove A times B is also in U so that closure holds. Now AB is in U, that means there exist A prime and B prime in U such that A prime is 1 and B prime is 1 because they are units. So that exist by the definition. Now AB times A prime B prime, what can you say about this? This is just A prime B prime, right? Because we are in a commutative ring. All our rings are commutative ring with identities. So this is just 1 times 1. So this is 1. So that means this product is also a unit. So the first property closure holds. And ring multiplication is already associative, right? By definition of ring. So we have nothing to prove in that case. And identity is 1. So let me write this. Since ring multiplication is associative, uh, so multiplication is associative on U, right? Because U is a subset of R. And we have identity element 1. You can check, it's very trivial. And 1 belongs to you is the identity element for the group, is the identity element. And obviously inverse element also exists by definition because these elements are unit. Also inverse of every, okay, of each element, of each element in U exists by definition. Okay, so this forms a group, and in fact this is an abelian group because all our rings are commutative ring. So just keep this thing in your mind. This is not very difficult. I hope you can understood. So I have introduced zero divisors. I have done one problem on that and one problem on this unit. Okay. Okay, let me introduce one more special type of element that is important. So that is known as nilpotent elements. I think you will you will get these notions in the upcoming weeks or maybe in the assignments. So it is better to learn. So what is a nilpotent element? So let R be a ring, then an element, let's say X belongs to R, is said to be a nilpotent element. Okay, so an element X in R is called nilpotent if X power n is 0 for some positive integer n. Okay, 0 means the zero element of the ring, which is the additive identity, means identity under the addition. So x power n is 0 for some positive integer n. So let's see an example quickly. So I will give the same example which I have given for these zero divisors. Or maybe I can change also. Let's take R to be the ring Z mod 4Z. So here 2 bar square is 0 bar. So 2 bar is nilpotent. Okay. So remark one remark is first thing you observe that nilpotent elements can be 0. So 0 is a trivially nilpotent element. 0 is nilpotent in any ring. So this is let's say this is 0th example and this is first example. Okay, so let's see the remark. Remark is every non-zero nilpotent element is a zero divisor. Okay, every non-zero nilpotent element is a zero divisor. Can you see why this is happening? Yeah, anyone? Okay, so let X belongs to R be a non-zero nilpotent element. Then we need to prove X is a zero divisor, right? So by definition of nilpotent element, we can write X power n is 0 uh, on multiplication with what? With itself. Not actually itself. Okay, let me write. So by definition, X power n is 0 for some positive integer n, right? Now notice that X is non-zero. So this n cannot be 1. So n cannot be 1. So that means n is at least 2, right? Because X is not equals to 0. So then you can write this as X power n minus 1 times X. And this is 0. And X is non-zero. So X power, okay, also we need to assure that X power n minus 1 is non-zero. So let me write it here. So X power n is 0 for some positive integer n, that we know. Let's take n be minimum such n. Let n be a let n be, okay, sorry, let n be minimum such that X power n is 0. Okay, so now we can say this thing. So I am saying now n is not equals to 1 because X is non-zero. So that means n is at least 2. So then X power n equals to 0 implies X times X power n minus 1 is 0, where X power n minus 1 not equals to 0. And this is non-zero because n is minimum such that X power n is 0. Okay, so I hope now this is clear for everyone. So this implies X is a zero divisor. So we are using the fact that X is non-zero. Then we have taken n is minimum index such that X power n is 0. Then from that we have concluded this. Is it okay? Okay, I hope all of you have understood. Okay, so let's go to the next problem. So problem number 3. Okay, so let R be a ring. So this has many parts. So this is the first part. So if X is an important element, okay, let X, if X belongs to R, is an important element, then Rx is nilpotent for every R in R. So if you multiply a nilpotent element with any element, that will give you another nilpotent element. So this is the first statement. Second, if you take two nilpotent elements, uh, every non-zero element is a zero divisor. Does this statement hold for any ring? It's for commutative ring. Uh, no, I don't think we need commutativeness for that, because powers of x always commute with itself. By the way, let's not talk about non-commutativeness, because here we are only taking commutative rings. If you have further doubts, you can ask in the end. I don't mind. Okay, so if you have two nilpotent elements, let's say A and B in R, then their sum is also an important element. Okay. So first I told that if you take an important element and product with it with any other element, you will get an important element. And in this case, if you take two nilpotent elements, then their sum is also an nilpotent element. Okay, the third one. So if X belongs to R is nilpotent, then the element 1 minus X is a unit. Okay, so I have one more statement, but let me prove this three first, then I will come to the last statement. So the first statement is, if X is nilpotent and R is any element, then the product is nilpotent. So let X belongs to R be nilpotent. And let R belongs to R be any other element. Now since X is nilpotent, So then x power n is 0 for some positive integer n. So this will imply uh, rx power n. So now this you can write as r power n times x power n, because we are in a commutative ring, and this is r power n times 0, this is 0. So this will imply Rx is nilpotent. Okay, so this is very trivial actually. So let's see the second one. So second one is sum of two nilpotent elements is nilpotent. So let's take two nilpotent element. Let A, B belongs to R are nilpotent. So we want to show A plus B is also nilpotent, right? So now if one of A or B is 0, then we have nothing to prove, because then A plus, if A is 0, then A plus B is A, so it is nilpotent, and same for B is 0. Then nothing to show, right? So assume that A is non-zero and also B is non-zero. Now from the definition of nilpotent, we can write A power n is equals to 0 and B power m is equals to 0 for some positive integers n and m, right? Now what is A plus B whole power n plus m? Can you say what will be this element? Okay, so we are in a commutative ring, right? So in that case, this element will look like summation k equals to 0 to n plus m, n plus m choose k, a power k, b power n minus k. So this is the usual binomial formula. So this thing holds in commutative rings. This you can take it as an exercise. This is not difficult to prove. You the way you prove the usual binomial formula, you can use the same thing here. Okay, now this is an element of the ring. So what can you say about this product? So if uh, k greater equals to n, then so if k greater equals to n, then a power k is basically a power n times a power k minus n, and this is 0 times a power k minus n, which is 0. Please repeat the previous point. Uh, Are you saying this thing or okay? So I am saying what will be this sum? How this will look like? So if you take a plus b, okay, let me take a plus b square. Then how you will expand this? So this is basically a plus b times a plus b. So this is just a square plus ab plus ba plus b square. Now we are in a commutative ring. So this element is equal with this element. So a square plus 2ab plus b square, since ab is equal to ba. So this is exactly the binomial formula, right? So similarly, you can write a plus b power q or any power, just any n. So this is just summation n choose k, a power k and b power n minus k. K is equals to 0 to n. That is the usual binomial formula. So I am saying in case of arbitrary commutative ring, this binomial formula holds. Okay, that you can prove in the same manner. Is it okay? Okay, fine. Okay, now look at this product terms. So we need to prove that this element is 0, right? So if we can prove that each term in this summation is 0, then we are done. So now if k greater equal to n, then a power k is already 0. Now what happens if k is less than n? Yeah, that should be n plus m minus k. Yeah, you are correct. So then this is n plus m minus k greater than m, right? So that will imply b power n plus m minus k, it will be 0. So in this product, every element is 0, whatever the case. So this right term, so the RHS of a plus b power n plus m, okay, every term in the RHS. So every term in the RHS of a plus b power n plus m is 0. So a plus b power n plus m is 0. So this will imply a plus b is nilpotent. Okay, I hope this is clear for everyone. So sum of two nilpotent elements is again a nilpotent element. So this proves the second one. Now the interesting part is the third one. So if x is nilpotent, then 1 minus x should be a unit. Okay, let's prove this. So let X belongs to R be nilpotent. Right. Now then X power n is 0 by definition of nilpotent element, where n is a positive integer. So we need to prove 1 minus X is unique. So that means there exists some R whose product with 1 minus X should be 1. So our goal is to prove the existence of R. Now you recall that if we take the sum of this 1 plus x square plus x power n minus 1, then what is this sum? So this is basically 1 minus x power n divided by 1 minus x. So if you don't know this, you just take it as an information. So this means 1 minus x times 1 plus x square plus x power n minus 1 is 1 minus x power n. Right. So let's use this information here. So let's look at this product. 1 minus x times 1 minus, so 1 minus x times 1 plus x square plus up to x power n minus 1. Now expand this. So first let multiply 1 with all term, every term. So that will give 1 plus x square plus up to x power n minus 1. Now multiply with minus x with every other term. So minus x times 1 plus x power n minus 1. Now expand this again. So this is 1 plus x power n minus 1 minus x square minus up to x power n. Right. Now you can cancel this x with minus x square with minus x square. So you can cancel up to x power n minus 1. So this will give you 1 minus x power n. Okay, I hope you have understood this. Now x power n is 0. So this is just 1. So we have found an element whose product with 1 minus x is 1. So 1 minus x is a unit. Is it okay?
Sir, can you please explain like what is the relation between unit and nilpotent element?
Relation between unit and unit and nilpotent element.
Yes, sir.
These are two different type of elements. So an element which is unit, that cannot be a nilpotent element. That I can say.
Okay, sir.
Yeah. Just a minute. হ্যাঁ বলো কেন পড়ছিলাম কেন ঠিক আছে রাখুন পর ফোন করবো। Okay, so I hope this proof is clear. So now let me write down the other statement. Yeah, any doubts? So I have just proved that if you take an nilpotent element, then 1 minus x is unit. Now the fourth statement is, let's take as B. So if x belongs to R is nilpotent, and let's say U belongs to R is unit, then their sum U plus X is also a unit. Yeah. Sum of a nilpotent element and a unit is a unit. Yeah. Can you prove this by using C?
Yes, sir. We can take x as nilpotent, and just now we have proved 1 minus x is unit. So
Okay.
sum will be 1. So can we prove like this?
Sum will be 1 means.
X plus 1 minus x. So we remain with 1, which is a unit element in R. Can we go with that, or a rigorous proof is required?
No, no, no. I am taking U is an arbitrary unit. You need to prove U plus X is unit.
Or
So, did you understood the question?
yes, sir, understood the question.
Yeah. So, what is your argument then? I'm not getting. Okay. So let me do the proof. So I will be basically using the part C. So so we need to prove sum of a unit and a nilpotent element is, so okay, I have already assumed that okay, let X belongs to R be nilpotent, and U belongs to R is unit, right? So then uh, U times U inverse means U inverse exists, right? Then U inverse exists. Okay. So by the first part, if we product a nilpotent element with any other element, it again a nilpotent element. So U inverse times X is a nilpotent element. Okay, this is by part A, right? And also we can take minus of this. Minus U inverse X is a nilpotent, because minus U inverse X is nothing but minus 1 times U inverse X. U inverse X is nilpotent and minus 1 is an arbitrary element. So this element is nilpotent. So now this implies 1 minus U inverse X is a unit. This is by part C, because this is a nilpotent element and 1 we are adding. So 1 minus U inverse X is unit. Now U is a unit. Okay, now U and 1 minus U inverse X are units. So their product is also unit. So u times 1 minus u inverse x is a unit. So u minus u times u inverse x, which is nothing but u minus x, which is a unit. So is it okay? Did you got the idea? Yeah, 1 plus x is also a unit because minus x is nilpotent. Converse of what? Can you converse of c? So what is converse of c? X is nilpotent, then 1 minus x is unit. 1 minus x is unit. Is x nilpotent? I don't think it is true. Yeah, it is not true in general. So you can one can try with some examples. Yeah, it is not true. Try to see some examples. That's a good question. Yeah, it's easy to find examples of this converse of C. Okay, I hope D is also clear. Oh, for D we don't need this part. Don't need this. Yeah, in Z plus you can take 1 minus 2 is a unit. Okay, so D is true. Now let me give you an easy exercise out of this thing. That is very easy, but consider this set. Okay, let me define as A. A is the set 1 minus x such that x belongs to R is nilpotent. Okay, then A is a subgroup of the group of all units of R. So I have already proved that the set of all units of R is a group. Okay, so I have proved u minus x is unit. Yeah, you can prove also u plus x because here you can, if you take uh, yeah, so minus u inverse x is also nilpotent. So then you will get here 1 plus, sorry, 1 minus u inverse x is unit. So this is basically 1 plus u inverse x. Now you multiply it with u. So that will give you u plus x is unit. Yeah, okay. So let me put this as minus, otherwise things are mismatched. Yeah, thank you for pointing out. Okay, so what I am telling is the remark, take this set A. A is 1 minus x, where x is nilpotent element. Then this will form a subgroup of the group of all units of R. So you take it as an exercise. This is very easy. Okay, let's move on to another problem. It's problem number 4. Okay, so in the examples, yeah, I will upload the PDF. So in the lectures, you have saw the ring of all continuous functions, right? So let R be the set of all functions uh, from real numbers to real numbers such that f is continuous. So then R be the ring of all the ring of all continuous functions. So I hope you have saw this in the lectures. Now this is a true false type questions. So then which is true? Which statement or statements? Okay, so there are two statements. You need to say which one is true. So this ring R has zero divisors. This is the first statement. Second one is R has uh, non-zero nilpotent elements. So you take the ring of all continuous functions. This forms a ring with just addition of functions, pointwise addition and pointwise multiplication. So now there are two statements. First says this ring has zero divisors. Second says this ring has non-zero nilpotent elements. So is this true? Both statements. Think for a few seconds. Yeah,
सर नीलपोलेंट एलिमेंट मतलब क्या होता है थोड़ा सा उसके बारे में
yeah, I have already defined. Its power is zero for some positive integer. Yeah, here I have defined. In a ring, if you take an element x, then x is nilpotent if x power n is 0 for some positive
यस
integer n.
सर अंडरस्टैंड सर थैंक यू सर
Yeah. Yeah, anyone or any guesses? So first, let's talk about zero divisors. So does it have any zero divisors? Okay, so can you give examples? So one student is saying yes. What about others? Uh, the function you have given is not continuous, right? I am talking about continuous functions. Yeah, but the approach will be same. So basically, you just look at the graph. So this is your x-axis, this is your y-axis. You just take a function whose uh, okay, I don't know about that function what you are talking about, but let's see this. So you just take a function as which gives value like this in the negative side, and in the positive side it looks like this. And you take another function which looks like this in the negative side and looks like this in the positive side. So we can also write this function. Let f equals to 0 when x is less okay, and it is exactly equals to x when x is positive. So this is the first function which I draw in the black color, and g of x is x uh, when x is less equals to 0, and 0 when x is positive. So this is the function which I draw in the green. So this one is your g, this one is your f. Now if you take the product, then f of x times g of x is 0 for all x in R, right? So that will imply fg is the zero function, but neither f nor g are zero functions, and this is continuous. It is clear from the graph, or you can check by the definition also or other things. So this statement is true. So I hope this is fine. Now what about the second statement? Second statement is much more easier. Yeah, any answer? Anyone? Okay, so let me do the second one also. So what will happen if there exists a non-zero nilpotent element? So let F belongs to R be a non-zero nilpotent element. So then F power n is 0 for some positive integer n. Now what is F power n? So this is basically fx power n is 0 for all x belongs to R. Now f of x is a real number and power of some real number is 0. That will imply that that real number is itself 0. Right? So that means f is actually the 0 function. That is contradiction. So there cannot be any non-zero nilpotent element in the ring of all continuous functions. Is it okay? Yeah, I hope it is fine for the others also. Proof of B. Yeah, it is basically by contradiction. You take a non-zero nilpotent element and yeah, I am taking the set of all real number, continuous functions over R. Okay, I hope this is clear. Okay, now let's move on to some other problems regarding subrings. We saw the result every non-zero nilpotent element is zero divisor. It has a zero divisor but not nilpotent element. Yeah, you are right. So every non-zero nilpotent element is zero divisor, but the converse need not be true. So this is an example for that you can take. Yeah, good observation. Okay, now subrings. So problem number 5. Before moving on to subrings, let me ask you a easy question. It's also a true or false. So the statement is some, okay, let R be a ring and A comma B belongs to R are zero divisors. Then A plus B is also a zero divisor. Sum of two zero divisor is a zero divisor. It is true or false? Yeah, anyone? True. Okay, how? Yeah. Any other responses? Non-zero element.
Is it false? Z6, if we can take an example of Z6 or Z by Z6, Z by 6Z. So elements, if we can take 2, 3. 2 and 3 are zero divisors, but 2
Yeah,
plus 3 is 5, which is not a zero divisor.
yeah, you are absolutely correct. So this is false. So as he is saying, you can take example. You can take the ring Z mod 6Z, and you can take the elements 2 and 3. These are zero divisors, but 2 bar plus 3 bar, which is 5 bar, is actually a unit, so it cannot be a zero divisor. So 5 bar is a unit, so it cannot be zero divisor. So I hope others also got this. So saying every non-zero element is a unit, so cannot be nilpotent. So I don't know how we were saying that every non-zero element is unit. I don't know that is true or not. Okay, let's move on to another problem.
Sir, may I ask one question?
Yeah, regarding
Zero divisors only.
yeah,
If a ring is containing, if a ring has all the element as zero divisor, then can it be considered as an integral domain or
a ring consisting only
of every element as zero divisors?
no integral domains are defined as which contains no zero divisors, right? So
All right.
yeah, I have not mentioned. Yeah, I will come to that.
All right, sir.
Okay, let's do an easy exercise on subrings. Every element in R is a unit, right? So every non-zero element of R is a unit. So every non-zero element of R cannot be nilpotent. Yeah. So what you are trying to conclude, I'm not saying. Yeah, here you can write because R has no non-zero nilpotent element. I don't know you are trying to saying this or yeah, that I have proved actually. You can check. Think. Okay, so let's move on to another problem. So let R be a ring and suppose that let's say S alpha be a family of subrings. Okay, so I'm taking a family of subrings of R, then their intersection S alpha is also a subring. So okay, we need to prove this. Okay, then prove that. So this is very easy actually, but one should know this. So this is saying if you take any collection of subring, then their intersection is also a subring. Okay, so so for subring, what we need to prove is first it should be a subgroup under addition, and it should be closed under multiplication, and 1 must belong to that set. These three things we need to check. So intersection of subgroups are subgroups that you must be knowing. Now intersection of S alpha is clearly a subgroup under addition. So you can go back to your group theory and check this also. And let's do the closure under multiplication. Now let a comma b belongs to this intersection. So that will imply a comma b belongs to S alpha for every alpha, and that will imply AB belongs to S alpha for every alpha, because S alpha is a subring. So this shows AB belongs to S alpha, intersection S alpha. So intersection S alpha is closed under multiplication. And also 1 belongs to this intersection. Also 1 belongs to S alpha for all alpha, implies 1 belongs to intersections of S alpha. This is a subring, so it's very trivial. Okay. Now what about union of subrings? Is it a subring?
Not necessarily. I think one should be contained in the another, then it is
Yeah, not
possible.
necessarily, but can you give some example? Union of subrings need not be subrings. Yeah, can anyone give some example? So some examples of subrings in known rings, which you have already saw in the lectures. Okay, let me give you. So you take R as the ring C and take S1 as the set of all real numbers and S2 as the set of all Gaussian integers. Right, both are subrings. You have already saw in the lectures, but S1 union S2 is not a subring. That you can check. It is not even a subgroup also. So that's trivial. Yeah. So any doubts?
No, sir.
Okay. So let's move on to another problem. Z the
Z can be taken as a ring. A ring be the set of integers. We can take 2z and 3z be the subrings of this. And when you take the union of 2z and 3z, so वो नहीं होगा. Union cannot be a subring because it is not closed under addition. 2 plus
yeah,
3 does not belong to me.
but you need to be careful here, because in this course we are assuming that subrings contains 1, right? So 2z and 3z are not subring in our assumption.
Okay.
So you need to be careful in that sense. Otherwise, your example is fine. So that's why I have already mentioned the assumptions in the beginning. Okay. Okay, so let me write the next problem. Let A be a subring of C. R union Zi is Z. No, that is not true. That is a simple theoretic thing. You can do it on your own. Okay, let's focus here. So let A be a subring of C such that R is subset of A. Okay, then prove that either A equals to R or A equals to C. Okay, so this question is saying if you take the ring C here and if you take the ring R here, then in between you cannot have any other subring. Can you try this? Yeah, anyone? So in between C and R, there cannot be any other subring. Okay, so it's look like proving maximal ideals. Not exactly that. You can say maximal subring, but I don't think there are such concepts. I don't know. But let's not go into that much deep. We don't need anything which we have not learned. Okay, let me prove this. So if A equals to R, then nothing to prove, right? Assume that R is a proper subset of A. So then we need to show A is equals to C, right? So A is properly containing R. So in that case, we need to prove A is equals to C. Now R is a proper subset of A. So there exists some A plus IB belongs to A with B not equals to 0, right? Because A is properly containing R, so it must contain some complex number. So that's why B is non-zero. And A and B are real numbers, right? Because that's how complex numbers look. So A and A plus IB both belongs to A. So that means minus A plus IB also in A because it's a subring. It is closed under subtraction, addition, all those things. So IB belongs to A. And also B is non-zero. B is non-zero real number. So B is a unit. Also B is non-zero. That implies B inverse belongs to R. That is subset of A. So B inverse belongs to A. So IB times B inverse belongs to A because it's a subring. So closed under multiplication. So that will imply I belongs to A. Right? So now 1 comma I both belongs to A. And also R is subset of A. So we can take all R linear combination of 1 and I. So that will imply alpha times 1 plus I times beta belongs to A for any alpha and beta in R. So this is alpha plus I beta belongs to A for all alpha plus I beta belongs to C. So this will imply A is exactly equal to C because it contains all complex numbers. Is it okay? Did you got this proof? Nothing difficult actually, it's simple calculations. Yeah, anyone? Any doubt? Okay, looks like there is no doubt. Okay, fine. Okay, so now let me formally define integral domains. That will be useful. Okay, so an integral domain let's say R is actually a ring which has no zero divisors. So an integral domain R is a ring which has no zero divisors. Right? So if a ring contains no zero divisor, then we call it a integral domain. So let's see some examples. So an example is you can take C.
Integers.
Yeah, you can take integers. You can take C also. You can take Zi. Let's restrict to this now. And the fact is, you can take any field. Field implies integral domain because a unit cannot be a zero divisor, and in a field, every non-zero element is unit. Now the last part is polynomial things. So let me go into that. So I hope you have understood the definition of an integral domain. So now one easy fact is a subring of an integral domain is also an integral domain. A subring of an integral domain is also an integral domain. And remember that our subrings contains 1, right? Without that condition, this statement need not be true. Keep this fact in mind. So let me do this proof quickly. So if S, okay, let S be a subring of an integral domain R. So in an integral domain, so the actual fact is it has no zero divisors, right? So that means in an integral domain, product of non-zero elements cannot be 0. So one should know this thing. So in an integral domain, product of non-zero elements are non-zero. Okay, that is the fact in an integral domain. Now let's come back here. So subring of an integral domain is integral domain. So let S be a subring of an integral domain R. We need to prove S is also an integral domain. So let A comma B belongs to S such that A is non-zero and B is non-zero. Now then A times B is non-zero in R, and since A times B in S and this product is non-zero, so A comma B cannot be zero divisors because these elements are arbitrary non-zero elements, and arbitrary, and I am taking product of arbitrary non-zero elements and I am getting this is non-zero, so this cannot be zero divisors. So S is a integral domain. I hope this is fine. Now let's go to another problem. Problem 8. So let R be a ring, then R is an integral domain if and only if the polynomial ring Rx in one variable is an integral domain. Okay, so R is an integral domain if and only if the polynomial ring is an integral domain. So I hope you have understood the definition of integral domain correctly. Do you have any doubt in the definition of integral domain?
No, sir.
Okay, I hope it is fine for others also. So let's prove this. So we need to prove two sides. So first, let me prove the backward implication. So let Rx is an integral domain. Right. Now R is a subring of Rx. Right. So clearly R is also an integral domain. Then clearly R is an integral domain. Because R is a subring of Rx. Okay. Now let's see the other part. Now assume R is an integral domain. So we need to prove Rx is an integral domain. Rx is also an integral domain. So what we will do is we will prove that product of every non-zero polynomial is again non-zero, so that uh, no non-zero polynomial cannot be a zero divisor. So let fx uh, equals to, let's say, a0 plus an x power n, and gx equals to some b0 plus bm x power m, b2 non-zero polynomials in Rx. Now these are non-zero, right? So we can assume an is non-zero and bm is non-zero. Their leading terms are non-zero. Now what is their product? So from this we can easily say that an times bm is also non-zero, right? Because these two elements are non-zero and R is an integral domain, so their product must be non-zero. Since R is an integral domain. Now if you look at the product, then how this element means, what is the structure of this element? This is basically a0 b0 plus a1 b0 plus a0 b1 times x, plus here degree 2 terms, and ultimately the last term is an bm times x power n plus n.
And
Yeah, and this term is non-zero, so definitely this product is non-zero. So product of two non-zero polynomial is non-zero. Product of two arbitrary non-zero polynomial. So that will imply Rx is an integral domain. Okay. So is it okay?
yes, sir.
So I hope it is clear for others also. Now let's do one more problem in polynomial ring. So let R be the polynomial ring Qx, means all polynomials over rational numbers. Then what are the units of this ring? Then what are the unit elements in R? So in this ring, which elements are units? Yeah, anyone?
Is it a constant polynomial in all the constant polynomial in Q of x will be unit?
Yeah, you are partially correct. You have to take all non-zero constant polynomials.
Yes, sir. Yes, sir.
Okay, so let's see a proof of this quickly. So in this problem I will be using one facts about the degree of polynomials. So before doing this, okay, let me do this. I will mention along we go. So let f belongs to R be a unit, right? Then by definition, there exists another element G such that the product of these two polynomials is 1. Product of two elements is 1. Now here we have the constant polynomial 1 and here we have two other polynomials. Now what can you say about degree of this left hand side? So that will imply degree of fx times gx same as the degree of the constant polynomial 1, and degree of constant polynomial is 0, right?
0. Yes.
And in the left hand side we have degree of fx plus degree of gx. So we can write this thing because qx is an integral domain, right? So I will mention this, don't worry. uh, Now from this we can say degree of fx and degree of gx both are 0 because degrees are always non-negative. So degree is 0, that means f must be a constant polynomial. So f is a constant polynomial. Constant polynomial means f must be an element of q, and also same for g. Okay, let me write here. F and g are and g times f is 1. So that means f belongs to q minus 0. So f must be a non-zero rational number. So units of qx are non-zero constant polynomials. Okay, so I hope you got this. So using the same technique, you can find the units of zx, rx, and other things.
Zx will have then only two this thing, na, -1 and 1.
Yeah, you are correct. Z of x has only two
For
units.
and for R of x, then there will be infinitely many this thing.
Yeah. So let me put this as remark. Let R be an integral domain. Okay, let R be an integral domain. Then by our earlier problem, the polynomial ring Rx is also an integral domain. Okay, and let f comma g belongs to polynomials of Rx. Okay, then the degree of this product okay, these are two non-zero polynomials. Degree of fx plus degree of gx. Okay, so degree of this product will be sum of the individual degrees. So you can try to prove this on your own. This is not difficult. But here important thing is we are in an integral domain. Otherwise this statement will not be true. You just try this and let me know if you are unable to do. So it's already time. So I think for today this is enough. So do you have any other doubts?
Sir, how to find out? Sir, I have a question.
Yeah.
How to find out the zero divisors of a polynomial ring? If you can take any problem,
If
small problem, zx you can take or qx, anything.
yeah, these are integral domains, na? So this cannot have zero divisors. Did you got? So if R is an integral domain, so Rx is an integral domain. So it cannot have zero divisors.
Right, sir. Right.
Yeah. Any other questions? So if there is no question, then we can wind up here.
Sir, one more question is one sentence if you can explain.
Yes.
If f of x is a polynomial in R of x, which
Okay.
has no roots in R, then f of x is a unit. Can you explain this statement?
If of x has no roots, then f
F
of
of
x,
x has no root in R, then f of x is a unit.
I don't know from where you have got this statement. I don't know also it is
Uh,
true or not.
I yeah, I got this statement in the assignment problem, so I didn't get this statement.
Okay. Uh,
F of x
so you are
belongs to
saying
Rx. F of x belongs
belongs
to
to
Rx,
Rx
has no root in R.
has no root.
In R, then
So f of
so
x is
x is
unit.
unit. Yes.
So a root means okay, an element, let's say A belongs to R, is said to be a root of,
If f of equal to 0.
yeah, if f of A equals to 0. So that is the definition of a root or 0 of a polynomial. So they are saying if it has no root, then it is unit or not. So you can check this statement, it is true or false. Yeah, this as because this is an assignment question, I cannot say something more than this. Okay, so you try to solve this. This is not difficult. You should do this.
Okay, sir, no issues. And sir, also one doubt I have, like, uh, the professor discussed two things, like how to divide a polynomial. One is like by synthetic division, and then he also proved one theorem,
Yeah.
like G alpha, if G alpha is a
Yes. Yes.
factor, something like. So I didn't get that one also. If you can just tell me in 1 or 2 minutes, if it is possible for you, that would
Yeah.
be a great help.
Okay. So I hope you know the division or division algorithm in the polynomial ring correctly. So the that statement is basically uh, let R be a ring, and you take the polynomial ring Rx. Okay. Take an element A in R, or as you are saying alpha. Let's take alpha. Take an polynomial Gx in Rx. So the statement is something I don't. Okay, I not recall now. Can you state that exactly the statement what it was?
I have to look for the notes that was provided by sir.
So one statement I can remember is that x minus alpha, this polynomial will divide g of x if and only if g alpha is 0. So that is something you can prove by using the division algorithm. It is not very difficult.
Yes, that's easy. And one more thing was there, no, degree of uh, degree of quotient should be less than the degree of remainder.
Uh, Degree of the quotient should be less than the degree of the
Degree of
remainder.
the quotient.
So if you divide fx by gx, and let's say qx is the quotient and rx is the remainder. So you are saying degree of quotient.
Q of x.
I think the other way should be true. Either,
Degree of Rx should be less than the degree of
yeah,
Qx.
either
Yes.
r is 0 or degree of r should be less than degree of q. Yeah, that is exactly the statement.
Yes.
Yeah, so what is the doubt?
So either we go with the theorem or go with the second thing, that is degree of R of x is 0 or degree of R is less than just. From both the things we'll be getting the correct answer.
Correct answer, which answer you are looking for?
No, it is there in the one question is also there in the assignment. So these are the two methods with the help of which we can verify. So what happening is, with the help of the second thing, that is degree of remainder is 0 or degree of remainder is less than degree of quotient. From this, all the options are getting correct, but with the help of am applying this theorem, only two are getting correct. So that was the
Actually,
question.
this whole thing is the part of the statement of division algorithm, right? So whatever assignment is given, I think that should be come from the division algorithm, I think.
All right, so I will go with division algorithm then.
Yeah, yeah. If you have further more doubts, you can put it in the discussion forum also.
All
Uh,
right.
yeah. Okay. Any other thing?
No, sir, I am done with the doubts.
Yeah. Okay. Anyone else? Okay. So if you have no doubt, then let's wrap up. Okay. Thank you then, everyone. Bye. Have a good day.
Thank you so much, sir.